So at equilibrium, we have rates of forward and reverse reactions are equal, but the concentrations are not equal. The numbers of people on each side of the river are not equal. Well, what can we figure out about those concentrations of reactants and products? Can we measure that or figure out what the ratio of reactants to products is? Well, it turns out that we can measure things like that, and one thing we use to measure this is called the equilibrium constant. This enables us to quantify the relative concentrations of reactants to products. Because it turns out if you do the same reaction but perhaps on a different scale, you do the reaction but you start out with twice as much reactant as you did in the first time. Of course, the concentrations are going to be different, but the relative concentrations of reactants to products will be the same every time, provided the conditions are the same. And so the equilibrium constant is what allows us to predict what's going to happen. So if we look at a generic chemical equation, so here we have A reacting to form A reacting with B to form C plus D. And these lowercase letters are standing in as variables for coefficients. So A could be 1, it could be 2, and so those are just standing in as variables. To calculate the equilibrium constant, we use this formula. So KEQ, the equilibrium constant, is the concentration of the products. When we put brackets around a chemical formula, that means the molarity, which we have not talked about yet, but it's a concentration. It's how many moles of that are in a liter of volume. So it's the concentration of C, and then it's going to be raised to a power. Whatever the coefficient is in the balanced chemical equation, we're going to raise that concentration to a power. So if this was a 2, if you got 2 moles of C, then this would be squared. If this C is a 4, then this concentration would be raised to the 4th power. So it's the concentrations of the products raised to the power equal to their coefficients, divided by the concentrations of the reactants raised to the powers of their coefficients, which it all seems a little crazy, but when we look at real equations, then it's not so strange. So if we were asked to write an equilibrium expression for this reaction, 2 molecules or 2 moles of N2O5 are in equilibrium with 4 molecules or 4 moles of NO2 and an implied 1, right, mole of oxygen. So the equilibrium expression then is the concentration of NO2 raised to the 4th power times the concentration of oxygen raised to the 1st power. So we didn't write the 1 here, we don't have to write the 1 there either. And then it's divided by the concentration of reactant raised to the 2nd power because this has a 2 in front of it. So the coefficients in the chemical equation become exponents in this equilibrium expression. Any questions? So let's do one here. Write an equilibrium expression for this chemical reaction. So KEQ, equilibrium constant, equals, it's always products over reactants. So our product here is HF. So I'm just going to take that formula and put it inside brackets. And what power should I raise it to? 2. 2 NF, so we've got, 2 HF, so we get HF squared. And then we divide it by the reactants. So we have H2. And what's the coefficient here on H2? 1. We don't have to write the 1 because it doesn't matter if we leave it in or out. And here we don't have to write 1 as the exponent because it's the same. Anything raised to the 1st power is just itself. And then F2 also raised to the 1st power. That is the expression, the equation to calculate the equilibrium constant for this reaction. And so what they've actually done is, people do all these reactions and they measure the concentrations very carefully, and then they plug the concentrations into this and they calculate KEQ. And you do this over and over and over and over again, and the KEQs will all come out really close to each other. They won't be perfect because there's error in measurement, but they'll do it like 100 times and then average the values together and say, okay, this is the equilibrium constant for this particular reaction. And then somebody in a different laboratory says, I'm not sure they did that right. I'm going to try that myself, because that's how scientists are. Kind of have an attitude sometimes. So they'll do it, and they'll either confirm the first scientist's work or dispute it. But in that way, people, it's kind of a check and balance thing. You publish your work, you put it out there so that other people can try it themselves. So that's how we end up with all these equilibrium constants. So what does that equilibrium constant tell us? Well, if that equilibrium constant is large, is that a big number? That's a really big number. 1.9 times 10 to the 19th is the equilibrium constant for this reaction. That's a really big number. That tells us that this reaction favors the products. Because the equilibrium expression for this, KEQ equals the concentration of HBr squared divided by the concentration of H2 times the concentration of Br2. So if this is a really big number, which experimentally they've determined it is, if it's a big number, that tells us that the number on the top, the numerator has to be large and the denominator has to be small. So large KEQ says we've got a lot of product, we have very little reactant at equilibrium. So we've got more product. If KEQ is small, for this reaction, KEQ is 4.1 times 10 to the minus 31. That is really small. A decimal point and 30 zeros for 1. Well, the equilibrium expression for this is NO squared over N2 times O2. If this equation is equal to a very small number, that tells us that the numbers in the denominator are big and the number in the numerator is very small. So a small equilibrium constant tells us that at equilibrium there are more reactants present. So in our population analogy, if the equilibrium constant is large, that means that there's a lot of people living in Middle Earth and there's very few people living in Narnia. And a small equilibrium constant is the opposite. Lots of people in Narnia, very few people in Middle Earth. Any questions? So here's the same explanation with pictures. So here's the equation, the chemical equation. Here's a picture of what this might look like at equilibrium. If KEQ is a large number, that means there's a lot of product and there's very little reactant. And if we look here, we've got one each of these reactant molecules, but most of it's product. So high concentration of product. When KEQ is a small number, in this situation, we see we've only got 2 molecules of product. Most of this is reactant. This reaction just didn't go very far. But this double-headed arrow, it tells us that the reaction is proceeding in both directions. And so there is reaction occurring, but the rate of the forward reaction is equal to the rate of the reverse reaction. And so overall, the concentration or the numbers of reactant molecules, the number of product molecules are not changing. They're just switching places. So, summarizing, if KEQ is very small, meaning a lot less than 1, the reverse reaction is favored. The forward reaction does not proceed very far. You've got a lot of reactants, very little product. If KEQ is big, the forward reaction is favored. We've got a lot of product and very little reactant. When the equilibrium constant is close to 1, and close to 1 in these terms would probably be between 0.1 and 10, as opposed to 10 to the 5th or something. That means that neither direction is really favored, and you end up with reasonable amounts of reactants and products. So you have significant amounts of both reactants and products. And the truth is that most chemical reactions are reversible to some degree, but the degree to which they are reversible varies. So if you get one if you get one with a really large equilibrium constant, you might not notice that there's any reactant left because it goes so far to the products.